So also hello and welcome from my side. So I will, together with Daniel, will give you an introduction into mass spectrometry. So we try to get all people to the same kind of knowledge, like on the same level that we all know in the end what we actually do, what we need to be aware of. And if people are already experts, I hope this will also get you some ideas to go back and think about some stuff that you already think you know, but maybe there's sometimes something somewhere in your mind. Yeah. And also, it's very nice to see you all here all together, and a big thanks to all people that did all this stuff in the back, like the planning and everything. So thanks to Madeline, I think as well, and Martin and Daniel. So thank you. So first of all, what's mass spectrometry and why is it so important? And one thing that we always need to keep in mind is that we measure ions, and this is very important to keep always in mind. We measure ions with mass spectrometry, and this is why you can see the scale here. So if we use the compound that we have, if we compare it with just and all the mass that we have, so the mass to charge, we see it's like equal. And what does it mean with the mass to charge ratio? If we combine like S, mainly carbon, hydrogen, nitrogen, and oxygen, then we get to this chemical formula, which then if we compute it to the neutral mass, then it's like equal to the compound that you see on the left side as well. And here I want to highlight why mass spectrometry is so important, or that we already use it in so many different applications. So for example, my group in Prague, we are working on specialized plant metabolites, but they are also working with microbes, with microbiome. And then, of course, we use it also as a quality control in schools or in the pharmaceutical industry as well. And what I think is pretty cool that we also use mass spectrometry in space. So we are not only limited on our Earth, but we also use it far away. And you see like how wide the field actually can be. And speaking about this, we always need to be aware what we actually study or what is our sample or our question that we have or an issue. So we need to see what is the sample set that we have and what is actually what we want to see. So we want to compare, for example, human samples compared to environmental, or if you go a bit like smaller, we use like the plant kingdom versus the microbes, for example. And then another thing is we need to keep always in mind what is actually our plan that we want to have. Do we want to quantify something? So for example, we have like a knockout study. Do we want to have like one compound that is not in any sample anymore, or do we want to see something with upregulation or downregulation? Or is it only important that we want to have it in one sample and it's missing in another? So this is something we want to quantify, or the qualification already enough. And then another thing, speaking about quantification, is like, is it targeted or non-targeted? I mean, with the research in the prenatal screening, of course, it's a lot of also finding by a target or finding targets for any disease. If we find the target in the end, it's non-targeted, but if we find something, then we can use it in a targeted way to search and screen like this blood sample as a targeted identification. And this is also something we need to keep in mind. Metabolomics is like a very already a specific field, or small molecules, it's also sometimes called. So it's very already specific. So we are only focusing on a specific field or study. And then it's also very important which instruments do we choose, what is the extraction method that we use. So we are already kind of biased how we actually extract the samples, and in the end how we actually analyze it, or which instruments we actually use. And therefore it's always very important to actually know what you are looking for. So if you use something that is hydrophilic, then we'll do some extraction that you actually extract your sample out, and then use the system that actually helps you to identify it. If you can't detect it in your system, of course it doesn't make any sense because you will miss it, and then you will be like, oh, it's not there, but maybe it's just because of the instrument and the settings. And that's why it's always important. There's no method that fits everything, so you always need to check what's actually my question, my research topic, and does this method actually fits what someone else maybe did in another paper, for example. And speaking about so many different stuff, so here's like a very easy setup what we can actually use as hyphenation. So maybe I can ask around who used GCMS for gas chromatography already, or maybe just in general who used mass spectrometry in general. How about GC? less people, then liquid chromatography. So yeah, interesting. And then of course something more specific is like imaging, who use imaging techniques. Okay. So we see it like less people. Oh, that's interesting. I think only 5 in total. So we see we have different platforms that you can actually use. We see GC and LC are like the most prominent, I would say. And imaging is very specific, but it's also a very nice field. So yeah, I also work a lot on imaging, so I also like this topic as well. And so far, we are also not only limited in these 3 techniques, we also have the ion mobility dimension. Maybe who work with IMS data already? I guess it's even less people. No, seems to be even more than imaging. Pretty interesting. So, and this is also some additional dimension, and now we can also combine IMS. So it's not only an individual part, but we can combine it with liquid chromatography, or we can use like imaging as well and combine it to IMS dimension, which is very nice because in imaging we don't have any separation because we only acquire like spatial on our sample. But with IMS, we could add like a separation to actually separate based on the spot our compound as well. But I will not go too much into IMS because I think it's also people use it less here as well. So what I want to make sure is we have seen so many different tools or hyphenation options and whatever, but in the end, if we see GC or LC, it's always for imaging. So we acquire mass spectra in the end. So we have like MZ compared to intensity. And of course, we have some additional information based on the system that we use. But in the end, the first thing that we should be aware of is that the mass spectra are kind of the same. Again, you put like in the end retention time as a different identification dimension and separation, and in imaging you have like the spatial control images as well. But the first spectra are kind of the same idea. And speaking about so many separation techniques, it's like with each technique you have like advantages and disadvantages. Of course, with gas chromatography, you have like the boiling point as the identifier, and it's only possible for volatile compounds. For liquid chromatography, we are more for the polar side, I would say. And then again, we have the retention time that we can compare. With ion mobility, we add the dimension of the size and the gas shape, which is also very nice to have as an additional identification dimension. And then, of course, we have the mass spectrometer to measure the mass charge, but to separate the ions based on their mass charge ratio. And then you see here a very easy way how to set up our system. We have our sample extraction system like LCGC. Then, of course, we need to ionize our compounds because we can only detect what we ionize. Or we can also transfer through the whole mass spectrometer what is ionized, so we can guide it based on the chart. And then we also have our ion analyzer, of course. We need to separate the ions right based on the mass, and then we need to detect those ions in the end. And then in the end, you can get like intensity MZ, which is like the most important step here, and then we can add retention time and particular cross section based on the setup that we use. And again, this is just a very brief what we can get out of GC, LC, and imaging techniques. Again, GC you can only use if the compounds are volatile. Of course, if you have something polar, you can use a derivatization reagent, and then it's like also volatile, but your compound needs to be very stable in a way. And then you need to be aware that in the ionization mode, so here we use electron impact, we fragment most of our signals. So in the end, we need to know which is our like precursor ion, but it's pretty hard to get to this. So you need to complete all your spectra to get an idea. So mostly we see fragments, maybe some N+. And with HPLC, it's a softer ionization in this case with ESI. So here we see mostly N+H or some other adduct like sodium, for example, or ammonium, depends what you also use in your buffers. And then we have multi, which is a very nice technique that you can use your tissue sample, for example, and then you can analyze it directly on your thin section. Here the ionization is also soft, so you see also N+H adduct, and maybe also other adducts depending on your matrix that you have in your tissue itself. And I talked already a lot about LC, GC, and so on. And here I want to highlight what is the basic idea about chromatography. And it's just very brief. So in the past, a lot of people use, for example, thin layer chromatography. So what's the basic to separate ions? and to separate compounds based on their interaction with the stationary phase and with the mobile phase. And then we see nicely in this image here that we see based on the color, the compounds are having a different retention on the silica gel. This is also one how it actually looks like. So we see the solvent is going and then it's taking the compounds based on their interaction higher on the silica gel or lower. Another step to separate compounds is you can liquid extraction, for example. So it depends how is separation, or how does it act in the lipophilic or in the hydrophilic way. So if you have an organic or water phase, how will it actually separate in your different phases? And then based on this, you can separate different compounds. Of course, you need to know where your compound will be in the end to get your compound in the end for the analysis. One nice thing, for example, if you have a compound that you can charge with a buffer, so you can first, if it's like neutral, you can have it in the organic phase. You take the organic phase, then you take the buffer to change the pH in the water phase. Then you charge it, and then it will be in the water phase. So you separate it from a lot of stuff based on this technique already. And then you have the solid liquid or gas extraction, is like basically liquid chromatography or gas chromatography. It's always the same. You have like a stationary phase and then a mobile phase, and then based on this affinity where it will stay longer, you will see a separation from the compounds in the end. This is just a very brief summary what things we can actually separate, or based on which setting or from the compound itself. We see we have the polar interaction, we have the boiling point of the GC. We can also use size exclusion if we think about macromolecules, but this is very specific. I think you can also use in LC and based on the column that you then use in the chemistry. And normally we use, like, for most applications, I would say, so we use reverse phase chromatography, and then we have our stationary phase with normally 18 length. And then we see that we have one compound here in the lower compound has like more affinity to the stationary phase, so it's slower diluting from the column. And then we have the second compound, which has like an hydroxy group, so it's more polar and has less interaction with the stationary phase, but more with the mobile phase. And then it's diluting faster than this one. We see the other one is already gone, and the lower one is still interacting and is reaching to later time point the end of the column. And this is just an example that there are more options. It's not only C18. I mean, C18 is still the most prominent one, I would say. Then you can sometimes see C8 is also used if you want less hydrophobicity, for example. Then we have phenol and also like shield options, but there you always need to check what you actually want to have. If your separation bad, you can change, of course, the solvent gradient that you use, or you can also try to change the color and use something that might be useful to separate your compound. And then I already said, so you have a compound that is like slower than the other. And if you want to get some ideas how good is our separation itself, so we see here like this is completely extracted. And then we can use different parameters of this chromatogram this chromatogram to get an idea of our separation itself. So we have the retention factor. I don't want to go into too many details. I mean, maybe most of you know it already, or you can also read it later, but the important part is that you have like the highest point from your chromatogram for your ion. And then you always need to know what is your time that the injection was happening and everything that was not retained is like eluding out of your system. This is what you use with T0 as well. And then you know everything that is not retained has a time of 1 minute, maybe it's a bit longer from 1 minute, and then you know, okay, 1 minute is everything that is not retained in the system, and then everything else should stay longer, or you could like check different retention factors. Then we have the selectivity factor where you actually compare two of these retention factors. And then of course we have the resolution that we can use. And then here we just need to be aware that there are different formulas that we can use. So we can use the half weight of the height and so on. And then we can get an idea about the resolution if we can separate two peaks that are close to each other, for example. And this is just, again, an example how actually a nice chromatogram can look like. Of course, the basic idea, if we use this, for example, as a standard, and we have maybe 5 5 compounds, for example, and then we want to separate all reference compounds that we have, and then we see like here 5 peaks, so we are good. And then of course we have like a washing step, so where everything else is coming out of the system. But this is basically the idea that we want to have, to separate all ions, or as many ions as possible, and then get a nice chromatograph out of it. And one thing I want to highlight is, in the past we used GC as this was the first method that we had. And the problem that we had in the past was, how do we get the solvent phase into a gas phase, right? So it was a big issue. So it wasn't so easy to put like a liquid into our mass spectrometer. And this is why the electrospray ionization was developed. So here we actually dry the liquid that is coming from the column entering our system. So we have this needle here. We have like different gases to dry it. We have a voltage. And then based on this, we get the charge and smaller droplets even evaporating even more. And then we get it into our mass spectrometer in the end. And then again, I want to highlight that based on the compound that we have different ionization techniques. I talked about ESI before, but of course not every compound is easily ionizable with this. If you have something that is more non-polar, there's also the option to use atmospheric pressure chemical ionization. I think this is a very nice visualization how it can look like, or what is the basic idea. So if you have something small and non-polar, maybe it's volatile, so we can use GC with it. But if we have something larger and it's polar, it's very promising that ESI might be a good setup to use. So coming to the mass spectrometer now. So we spoke about the separation technique, a very brief one about the ionization. And then if we think about the MS, so what do we get? The thing is, what we always need to know is we get normally the mass spectrometer acquires the data in the profile mode, what you can see on the left side, which has a lot of data points. If you think about every mass has multiple data points based on this or based on the distribution. So the normal way is then to convert it to centroided mode, or you could also set it already during the data acquisition. So the system will then already recalculate this into the centroided mode. Of course, the problem is you can always miss something, I would say, if you already convert something before actually getting it. So it's always nice to get like the real raw data, and then we will centroid it afterwards. So here we see that for each mass, we basically have only one signal. And this is also something we need to be aware of. So this is showing something very nicely from an isotope pattern. So we see each signal here has the mass difference of 1.0034, for example. So we see different isotopes for each signal or for each compound that we have. And then, of course, we also get different adducts, maybe in-source fragments. And this is also something we need to be aware of, because if you think about, you have some settings in your spray, you have like a high temperature. If you have glycosidic compounds, it is very promising that you will leave it off and you will only see the aquicon in the end. But of course, if you do the annotation in the end, you will also go to this later. Then you need to be aware, based on the settings, you can already break your compound to smaller parts, and you will use the original ion as well. But just something here's what I want to highlight is that you get always like redundant information about one compound. So it's not only you get one signal, and then it's good, but you get like multiple adducts, input fragments, and also isotope pattern, which is also nice because it also confirms a bit from your structure in the end, right? Because you get an idea, you see it's the active H, but not the active sodium, because you also see a signal in this mass change. Something else that you very often see in proteomics, or when you have macromolecules, is that you see multiple charged ions. In metabolomics, I think you mostly see doubly charged maybe, but in proteomics you actually see like 14 charges. And what we here need to be aware of, that we need to, because it's always mass to charge ratio, so the charge is always also in this hidden. So we need to then equally move the charge state based on this. So if we want to know the neutral mass from this signal here, we need to multiply it by 14, for example. And also, if you think about the isotope pattern will be also also changed. So if we go back to this slide here, where I said it's always 1.0034 for the C13 isotope pattern. If we have a doubly charge, of course, the isotope pattern will be shifted by divided by 2, so it will be 0.5 as again shifted, which is also a nice hint that we have a doubly charged ion in this case, because we have the isotope pattern in this shifted way. Another thing, what is very important if we speak about mass spectrometers, is that we have also this mass resolution from the from the mass side. So before in chromatography, we had like the resolution from the chromatography system, but here we have it from our mass instrument. And this is something I just acquired for copying with our Orbitrap instrument. I could set like different resolution, and what we actually see is that we change the peak width of our signal. Of course, if we have something, there's nothing surrounding it, we don't have any issue with it. But if we have some ion closer to it, then it might be a problem. But we see that we also have like a shift from the ppm value. Of course, if we have a wider peak, it's more harder to get to the highest weighted point. And then based on this, we get the shift in the end. But we see with the Orbitrap at least, and it was freshly calibrated, we see the ppm is still 1.5, so it's not that bad. If you think about the resolution, it's always, if you set it higher, your scan rate is like slower because you need more time to scan your ions. So this is also something you need to be aware of. And I mean, in this case, there's nothing surrounding it or interfering with our copying, which is not a problem. But if you look at this plot here, you see with different mass resolutions that at one point we get to this point where we can't easily separate the masses anymore, which is then a problem. And if you then think about that, you already convert your profile data to centroid data, maybe based on the centroiding algorithm, you will already combine some peaks that you would maybe in the profile mode still see a separated one, but based on the algorithm in the end you see only one. Maybe shifted and you think it's something else, and that's why it's maybe sometimes good to have the profile mode. And I know that there's a lot of discussion how to handle profile, because normally we use the acquired in profile, and then we already centroid it, and then no one is checking the profile mode anymore, right? So this is something I want to highlight, that this is actually important to check if there's something with the mass resolution happening or if it's too close. And yeah. Something else I also want to highlight in combination with the mass resolution, if you write a paper about it, how do you actually want to give the number, or how accurate is your number? And this is something I really want to highlight. Even though your mass spectrometer says, oh, I have this number of digits acquired, is it really true? So if you have something with low resolution, you can't just use any digits that the system is saying. So you should be aware that your accuracy is not that high. So maybe you can say like 1 digit. If you have done a Q-top, if it's already a bit higher in the resolution, you can add like 2 digits more. With Orbitrap, again more. And then if you go to FTICR, for example, you can even add more. But this is something you need to be aware of. Even the system says 5 digits and it's a triple quadruple, maybe check it and see if this is actually true, and then just use some less digits in the answer. Okay. And this is just a very brief overview which different systems we have and what is actually important. And maybe some people are like, oh, we only have a triple quad or a Q-top. I always want an Orbitrap. I mean, every system has the advantage, disadvantage. I would always, of course, you're limited to the system that you can have in your lab. And again, it also is good, and it's good enough to go with your sample. I mean, of course, you need to see what you're actually looking for. Maybe a collaboration partner has the system. It's something that is most of the time also very nice. If you do like a method development, you can use a system that is maybe less frequently used. At least it was in our old lab like this, so all people wanted to use the new machine. But maybe especially for method development, I think it's still nice to use the machine that is maybe not so occupied. You can do the method development, and then maybe if you want to have a paper out of it, you can switch and have the real samples running on the system in the end. So what I want to highlight is that each system of course has a different price, which is also important. If you use the Q-top, it's pretty fast in scanning, so it's very nice to acquire a lot of scan. It is very good for targeted analysis or accuracy, and you have a very high linear range. But if you go to Orbitrap, for example, of course, it's more accurate. But if you compare it to the scanning speed, it's like pretty slow compared to the Q-top. So this is something we need to be aware of at the end. And speaking about this is also a slide some people already knew maybe. So it's like, if you think about the mass spectrometer, everyone has their disadvantages and advantages. It's like if you compare it with the Pokemon cards here, you have like different resolution, accuracy, sensitivities, scan speed, and of course the cost, so not every lab can handle to buy this nice new machine for millions of dollars, whatever to buy. So this is also something you need to keep in mind. So coming to the more characteristics now, so I want to speak about some mass analyzers. So we have the quadrupole, which is very nice, I think. So what you need to be aware of is quadrupole. So in the name, you already have that we have 4 electrodes. And then always the opposite side has the same charge. And then based on this, we can actually move the ions in this particle, in this particle system. Which is also very important again. Ions we can move or we can maneuver through this way, but if we have some neutral ion, of course we can't do anything, so it will just go on, which is also nice because later the detector can't differentiate between neutral ions, whatever, so it's that we can actually guide then ions through this path and get only the ions from the master charge ratio that we're actually considering. So this is how it then works. So we have our positive charge ion here, for example, it's attracted by the minus charge, and then again we switch the polarities, and then it's like happening in a specific frequency, and based on this we can actually keep the ions on the way. And this is then also a nice way how we actually use the protocol very often. If we have a triple prod here, in this case, we can use like multi-reactor monitoring. So we use an MS1, we can select one mass here, the green circles. In the second protocol, which is a collision-induced dissociation trap, we can already fragment the round green things. And then in the MS2 again, we can set it to a specific master charge ratio what we want to track. And the example here is like this, the smaller round thing, and then based on this we can actually use this for quantification. It's very nice. And there's something to highlight here. And then of course if you want to use multiple reactions, you need to run it like every time you run. So here in this case you would have to have like 3 runs, for example. And then you can use like 2 other masses in the MS2 scan as a qualifier to see if the ratio is still the same and if everything was correct on the fly. So it's very nice here in this case. So you use 3, for example, reactions, and then use this as one quantifier and 2 as a qualifier in this case. And then another thing what you can also do, of course, is you have here in this case an ion trap. So you can not only select like one charge or one mass to charge ratio, but you can actually scan like the whole range of ions, which is also very important to know. So the next thing is when we have the protocol, and now we can also use the time of flight mass analyzer. So here we actually guide the ions through this path here, then we stop them a bit, and then we accelerate them all together as a bundle into the time of flight flight thing here, the tube. And then in the end, we can separate the ions based on their flying time. So this is shown here. So if you have MS1, we combine them or we stop them to have the same starting energy kind of. And then we see that the smaller ions are actually faster than the bigger ones. And then this is how we get the mass vector out of it. And again, if something is more abundant, of course, that means that we have more ions in this case. And this is then also nicely shown in our mass scan in the end. So this is for the top instruments, and if we go to the Fourier transformed instruments, so we have the orbit trap on the left side and the ion cyclical resonance mass spectrometer on the right side. These are very specific types of instruments. So we see here, I don't want to go too much into detail, but we actually detect all ions at the same time based on this Fourier signal. So the ions are moving in this direction, for example, in the orbit trap, and then giving a counter current, and then based on this, there's some calculations from the computers, and then we get the mass vector out of it. So we actually see how many processing is already behind those things. So this is also something you always need to be aware. When you see raw data, they are of course not any raw anymore because you have already some computational algorithms and optimizing in this steps as well. This is the whole setup. So we have our column, the ions are entering the C trap and then going into the orbit trap. And then you see we have like the spinning around this way, but this is the most important part from the left to the right, which is then giving us the counter current, and then we get our mass spectrometer, our mass scan out of it. And speaking about the C trap, I already started what we need to be aware of. If we think we have like a small space and we put all ions into it, we will have a big problem because we will have a problem. And I mean, this is nicely shown in this video. And I know that Daniel, for example, liked this video a lot because it's also highlighting what is actually the problem. So if you have ions, and we try to get it into this little space thing. We see, of course, it will not work because it will be overfull. It's, yeah, you will have phase charge effects, so the ions will interact with each other, the accuracy you will lose. We even had it in our system that we could separate two very narrow ions, but if we injected more of this, then we had like the, the problem that in the end it was like one middle mass because everything was interacting with each other. And that is why we have the C-trap, which is then actually checking how many ions are actually entering. So you can set it in your method, which is with automatic gain control. And based on this setting, it's like checking, okay, now I'm full, and I will send the package to the Orbitrap, and I will do the analysis, which is very important. Something else you can set, so I think also Daniel maybe will cover it later, is if you have this automatic gain control, but if you will not reach it, you also set a limited time, because otherwise it will run forever, way forever, but you can also set a time and say, okay, you either reach this target or the maximum injection time, and then you're good to go. You're not waiting forever, so you can acquire the next scan. And also in an Orbitrap, of course, we can do fragmentation experiments, which is only possible like in a targeted way if we have a protocol before, what we already talked before. So here we can set a specific mass to charge ratio what we actually want to have. And then based on this, we have like a mass that we know, and then we can acquire fragmentation data. If you think about this, is was maybe for a Q executive. If you think about an executive, there's no Q in the name, so we only had the Orbitrap. So there was no mass selection before, so you actually fragment everything on the same time, and then of course you need to go back and know, okay, what might be my precursor in this one? It's then comparable to GC, so you basically fragment everything on the same goal, and with this you can say, okay, I want to fragment this ion or this mass range, and then you have an idea what is your precursor ion. Speaking about this, so what are we actually doing in fragmentation experiments? I already talked about in this multiple reaction monitoring or in the precursor ion or product ion scan. So what this actually means is if we have the protocol before, so we can select an ion, in this case, this blue-greenish bubble here. Then we have some energy we put on the molecules to get it in smaller fragment pieces to get more information about the substructure itself. And then we can analyze those fragment patterns in the end. And again, if we see like the abundance again says something about the stability of this ion, for example. So if we see something like this means that then the fragment is more stable than maybe some smaller ions. And then of course, if you use higher energy, maybe you shift it to some other smaller masses. Maybe you lose some of the higher, because then you also break this one into smaller pieces. And then with this information, we actually know more about the structure. So if you think about, we only have the mass to charge ratio, the isotope pattern, we know already something about the structure. But if you want to know really more about the structure, this fragmentation pattern is really important. So here you get like smaller pieces of the structure, and then you know, okay, this part can only be because of this specific structure, and then you put everything together in a way that it makes sense. And this is also something I want to highlight with the annotation confidence. We still have a problem that there's no real standardization for the annotation rate. And this is something that was like published and is kind of used in the whole, not the whole metabolomics community, but at least the bigger group uses it. But for example, the environmental part, they have already like level 5. So, and there's also something, which level would you actually state, right? I mean, level 1 is always you have the highest level, you have the reference standard, you run it on your system, the same setting. So you have the retention time, you have the fragmentation pattern. And this is then when you say it's like a level 1 annotation. Level 2 is if you don't have the reference standard, so you can do library matching, which I think is most of the time the cases, because we will not have a standard for everything. So you use then level 2, you get like an annotation based on this library matching. But something here I also want to highlight, just because it's a match, it doesn't mean it's your compound. So it's also something you really need to check and be aware, even it's pretty similar to fragmentation pattern. Does this make any sense? So is the compound really in my sample? So if you have like a plant sample or some natural sample, and then you have something synthetic compound in it, is it really the compound in it, or is it just something that might fragment similar? So something you need to really check and not just say, okay, I have a very nice match, I have a high cosine similarity, and this is my compound that I will have. So always check the data, does it make sense, and maybe verify it in another way as well. Then we have like the levels that are less yeah, you don't really know what it is. So in level 3, for example, you get like a formula and maybe the molecular class, so you at least know which which group it belongs to. And then with level 4, it's like the lowest, you know the retention time, then Z, you know the feature, but you don't know what it actually is in the end. And just to know that this is something you need to know if you publish a paper, how should people know what is your confidence in annotating those compounds, right? I mean, it's always easy to say, oh, I annotated, I don't know, 50% of my sample, but is it really annotated or even identified? So even with identified and annotated, you need to be very careful, because identified is very, I know what it is, and annotated, yeah, it might be this, but I'm still like not 100% sure. And speaking about like fragmentation patterns, so I talked about MS2, but there's also the way that you don't need to stop at MS2, for example. So if you want to get more substructure information, because if you think we fragment some like glucoside compounds most of the time in the fragmentation pattern, you will lose your glucoside, and this is the main signal in the end in your fragmentation pattern. So it's not very rich. You don't know a lot. You know, maybe there's a glucoside, and then you know something about this the aglycon. But this is something that you can then use if you have like an ion trap. So there we can actually do multi-step fragmentation. So we don't stay only on MS2. So we have like the MS1 scan. We search for the highest signal maybe, we fragment it, but then we can do the same again. So we can use in the MS2 scan the highest signal and fragment this further and further. Of course, there's also limitation because each time you fragment, you lose ions, so you lose intensity. Of course, there's a limitation. Even the provider or the vendor even says, oh, our system can go to MS8, 9. Yeah, maybe you can, but maybe then the fragmentation pattern looks very weak. You have only noise maybe in the end. So this is something also to be aware of. And this is how a spectrometry can then look like. So this is just a very easy example. We have MS1 data, we pick like this mark, and then based on this fragmentation pattern in MS2, we then pick these 3 signals, for example, for MS3, and then based on their fragmentation pattern, again, the high signal. Of course, you will have sometimes redundancy, what you can see here, of course, because in the end, you see only the fragment signals that have the charge in the end, right? So everything else, if we have a neutral loss, it's gone. So we will not see it. And this is why, of course, with the substructure part, we are kind of limited to specific parts. And you can only see the stuff that is then keep the charge and that you can see the end. And this is also something you need to keep in mind if you acquire data in positive or negative mode. Maybe you see some fragments only in negative mode because the charge of the minus remains on the other part, like we have, for example, in lipids. And yeah, this is something also we check positive and negative spins as well. And now we talked a lot about fragmentation pattern, but how does it actually work? And I will give this part to Daniel.